Hello team, today's topic will be RCDs, residual current devices. One of my very favourite topics and something that I'm sure you have all heard me banging on about before because I love RCDs. I think they're a great invention and I think we should use them all the time, everywhere, even where not necessarily required by law. So what that means is I think the majority of the content of this will have been covered before. We've just talked about RCDs a lot in general throughout our course, so that information should be in our brains already. I'm just going to use this as a quick recap. I think we will get through this one in a single video, and so in order to make sure that that is not too long, I will move through this pretty quick. To that end, the first digit of your access code for the test will be 1. First digit will be 1. This is going to be a 3-digit code, and the first digit of your 3 digits will be 1. If I manage to do this in one video, I'll just do the three digits as we go through. Okay. As I said, I won't go into a great deal of detail on stuff that we've covered before. So this here is section 2.4.2 of ASNZS 3000. This is something that we have covered before. This is straight out of the standard, and it tells us about disconnection of supply. Disconnection of supply in order to keep people safe and protect property and so forth. So this is the rules that we need to follow, and one of the ways that we conform to that rule is by using an RCD. So automatic disconnection of current can be provided by an RCD. Here is a list of, again, straight out of ASNZS 3000. This is section 2.4.3. You can look that one up if you need to, but this gives us a list of the type of devices that we may use in order to comply with the previous clause, which talked about automatic disconnection of supply. Note D, fixed setting RCDs, complying with these standards here. So we can use RCDs as one of our methods of automatic switching off of supplies. And also note, rewirable fuses should not be used. Remember that one. Okay, section 2.6.3.1, residential electric installation. So this applies specifically to domestic installations, houses and stuff like that, right? Apartments, anywhere that people are going to live. So what does that section say? Again, this is out of ASNZS 3000. Absolutely feel free to look that up should you wish to do so. Additional protection by RCDs with a maximum rated residual current of 30 milliamps shall be provided for final sub-circuits supplying one or more socket outlets and lighting points, and directly connected handheld electrical equipment, for example, directly connected hair dryers or tools. And there's a note there on subclause B. For the purpose of this clause, combination fan, light and heater units, smoke detectors, exhaust fans and ceiling sweep fans are all regarded as lighting points. Okay, what does it mean? What does it all mean? Right, so we need to have RCDs. Where do we need to have RCDs? Well, section 1, subclause 1 tells us one or more socket outlets. So if I've got one or more socket outlets connected on a circuit, I must protect that with an RCD. Easy. If I have any lights on a sub-circuit, they must be protected by an RCD. As I said, for the purpose of this clause, a combination fan, light and heater unit, that's what you see in your bathroom, right? It's got the 3 switches, it's got the heat bulbs, it's got a light bulb, and it's got a little extractor fan in it. Those combination units, they count as lights. Smoke detectors, you can have, particularly off hardwired security alarm. You can often have smoke detectors that are hardwired to 230 volts. They count as lighting points for the purposes of this. Does it mean they're lights? No, it doesn't. What it means is you must use a RCD. They must be protected by an RCD. Exhaust fans and ceiling fans. So any exhaust fans, that's going to be your range hood. It's going to be exhaust fans in your bathrooms that take the steam and moisture out. Ceiling sweep fans are going to be the big ceiling fans, right? Cooling fans on your ceiling. They're regarded as lighting points. Again, does that mean they're lights? But does that mean they're lights? No. Then we've just put that in there to include them as part of the things that require to be RCD protected, so they must be on an RCD. Directly connected handheld equipment. So if you have a hairdryer or tools or anything like that that's directly connected, so it's got to be handheld. It has to be connected directly to the supply via a PCU. I can't think of too many things off the top of my head that fall into that definition. I mean, obviously a directly connected hairdryer or tool, of course, but I mean, how many of us have those? I don't. I've never seen them. But if such a thing exists, if you have a directly connected handheld electrical equipment, that must be protected by an RCD. So what doesn't need to be protected by an RCD? Well, everything that's connected on a socket outlet has to do that according to section A. And every lighting point has to. Okay, so what does not fall into that? So it's going to be things that are directly connected. Although section C says directly connected handheld electrical equipment, so it would have to be something that's directly connected, that's not supplied by a socket. It's not a light, or it's not part of those other ones that are included as lights. And it's not handheld. So what falls into that definition? Well, off the top of my head, things like an oven. An oven is directly connected. It's not a light. It's not handheld. So that doesn't need to be protected by an RCD. Dishwasher or the old waste disposal unit, possibly. Although most of the time, those will be connected by a socket and therefore would need to be protected. If they were directly connected though, then you could argue they don't need to be protected. What's the other one that I was thinking of? Hot water cylinder. Hot water cylinder, obviously that's directly connected, so it's not via a socket outlet. It's definitely not a light. It's definitely not handheld, so that does not need to be protected. Air conditioning units or heat pumps. Again, they're going to be directly connected, not handheld, and definitely not lighting. So those are the sorts of things that do not need to be protected by an RCD. And in most cases, you'll find that they are not. Although that doesn't necessarily say that they shouldn't be. It's probably mostly the current requirement that makes you want to not connect to those ones. My phone on silent. Sorry about that. Yeah, so we'd need some pretty big RCDs to power our oven. It's not commonly done, but actually when I think about it, I don't know why. Why wouldn't you just protect the oven anyway? If it's made of metal and it could become live, then people are definitely going to touch it. So let's protect it. I don't know. It's not done normally. It's not required to be done. That's the thrust of this. Okay, other electrical installations. Additional protection by RCDs with a maximum rated residual current of 10 milliamps shall be provided for sockets in areas within a building primarily for the purpose of teaching or caring for children in kindergartens and daycares and schools for children up to and including school year 8. So what's that up to and include? So that's intermediate. I think year 9 starts at high school. High school starts at year 9. So primary and intermediate schools require all socket outlets in teaching areas of kindergartens, daycares, primary and intermediate schools. And this is section 2.6.3.2 of ASNZS 3000. Have a quick think while you're sitting there before I go to the next slides. Have a quick think about what other areas do we need to have RCDs, because I guarantee you there's more, and we've talked about these before too. All right. 2.6.3.2.2 goes on to tell us where an RCD is required by ASNZS 3000 2.6. That's paragraph 2.6. To be installed to protect children, the RCD is deemed to be electrically unsafe if by children in kindergartens, daycares, primary schools up to year 8. The rating must be the following. 1 times current rating, 10 milliamps, 300 millisecond tripping. 5 times current rating, 50 milliamps, 40 milliseconds tripping time. If operated at 50% and less, it's electrically unsafe, less than 5 milliamps. Okay, that's a confusingly worded sentence. What that tells us that at 1 times the current rating in these areas, the kindergartens, daycares, and primary schools, At 1 times the current rating, which was 10 milliamps, it must trip within 300 milliseconds. At 5 times the current rating, so at 50 milliamps, it must trip within 40 milliseconds. And if it trips at 50% or less, then it's considered electrically unsafe. So it must not trip at 5 milliamps or less. Okay, an RCD installed as part of an installation to protect against electric shock to patients during patient treatment is deemed to be electrically unsafe if the rating must be again, confusingly worded, it's over. 1 times the current rating, so it's going to be a 10 milliamp RCD again. This must trip at 40 milliseconds. Note the difference here. So in child areas, 300 milliseconds at the rated current. In a patient area, it's 40 milliseconds at 10 times the rated, 40 milliseconds at the rated current, 10 milliamps. It's also 40 milliseconds at 5 times the rated current, so slightly more stringent in the medical areas. If it operates at 45% unless it's electrically unsafe, so if it operates at 4.5 milliamps, that is unsafe, that is not allowed. If you're thinking on the last slide when I said what are some of the other areas and you thought, oh, medical facilities, patient treatment areas, well done, there it is there. Patient treatment areas also require RCDs, which we've covered before, obviously, when we've talked about patient areas, medical and patient areas in the module that was specifically about that. Okay, residual current devices, RCD. It's a device for isolating supply to protected circuits, socket outlets, or electrical appliances in the event of a current flow to earth that exceeds a predetermined level. It does not provide overcurrent protection for the circuit. The usual fuse or circuit breaker protection for overcurrents in the circuit is still required. We know this, right? We know this. If we have a small current flow to earth, a low current flow down to earth, the RCD is going to pick that up. It doesn't provide normal overcurrent protection for the circuit. We still need our normal RCDs or fuses or whatever it is to do that. Unless we have an RCBO, right? Which we know that's a combination of a circuit breaker and an RCD. Residual current devices are protective devices that disconnect the supply to socket outlets, lighting, or electrical appliance subcircuits when they detect current leakage to earth exceeding a predetermined milliamp value. And obviously that milliamp value is the rated value of the RCD. Again, for what we just talked about in medical areas or child teaching daycare areas, it's 10 milliamps. For normal domestic situations, 30 milliamps. That's the predetermined milliamp value, this one here. Where there is a connection between the neutral and earth in an electrical installation, there is a chance that current will leak from the phase or live conductors to earth metal or the earth mats and flow back to the supply source. So if we have some sort of connection between phase and something metal, some metal part of an electrical appliance, and we have a connection between earth and neutral in our installation because we have an ME endpoint, that's the whole basis of our ME system, that means that current could then flow from that phase down through that metal, through the earth conductor, back across the connection between earth and neutral into neutral, which means we've got current flowing, which means we have a voltage present on that earth metal or on that metal, which means I can touch it and get a shock. Current leakage can occur if conductor insulation breaks down or if a live conductor makes contact with the metal in case of an appliance, or when a phase to earth fault develops within the installation wiring. A similar leakage situation can also occur when a person touches a live part while they are in contact with earth or any earth metal. To reduce the risk of electric shock and electrical fires, it's important to detect these small values of leakage current and quickly disconnect the faulty circuit from the electricity supply. RCDs are specifically designed to detect small values of leakage current and quickly disconnect faulty circuits or appliances. Yeah, okay. All of that's pretty straightforward. I don't think I need to explain that any further, and certainly this is all stuff that we have come across before. None of this should be new. This is the purpose, the function of an RCD. It's what they are for. Okay, some common names for RCDs. So see, these are some of the other names that you will come across, and it's important to remember these because different people will refer to them in different ways. In New Zealand, we usually call them RCDs, right? and you would have heard me talk about RCDs. They can also be called earth leakage circuit breaker, an ELCB. That is, it's reasonably common. You will hear them called that in New Zealand. I think it might be more of an Australian thing. Residual current circuit breaker, RCCB. That's not one I've come across a lot. Ground fault interrupter, GFI. That's a very American one. So often you'll see that if you're like me and when you encounter a problem or you're not sure about something, first thing you do, jump onto Google and see what you can find. And often you'll find forums, Reddit, places like that where people, real people are discussing stuff. That's where you'll find answers to your issues. So it's actually really common. It's a great way to find out information. It's go onto forums, Reddit, that kind of thing, and just see what people are talking about, or ask the question. Because a lot of the internet is American centric, you'll find that they often use American terms and definitions. And ground fault interrupter, or GFI, is one that you come across quite frequently if you're looking at electrical forums or electrical information out of America in general. They'll talk about GFIs, and that means RCD. Core balance earth leakage circuit breaker, CBELCB. Okay, I've never heard that one in my life. In fact, I've never read that until right now. But okay, we'll just agree. We'll agree that exists. Somebody uses it somewhere. If you ever hear that, then that's what it is. CBELCB. The common types of RCDs that meet the mandatory values for personal protection are RCCB, a residual current circuit breaker that does not incorporate circuit overload protection. So that's our normal RCD. It will trip a residual current fault or an earth leakage. Does not have any sort of overload protection or overcurrent protection. An RCBO, we've talked about these before, a residual current breaker overload, incorporating integral circuit overload protection within the device. What does that mean? It means it's an RCD and it's a circuit breaker. They go together. These are quite common or useful in situations, very small installations where you only have a single breaker. Garages, quite often in relocatable installations, your camper van or something, you only have one circuit breaker. You've got an RCD and a circuit breaker. That's all that's in the switchboard. So you just have an RCBO in a single, what you call a single one-way or two-way switchboard. It's just a tiny little, it's not even a switchboard, it's just an enclosure with a RCBO in it, and that does your circuit protection, your overload, and it does your RCD at the same time. PRCD, portable residual current device, which is usually an RCD incorporated into a plug or a cord set. These are voltage dependent, meaning every time the supply is taken away, the RCD will trip. So before every use, IOW, I don't know what that is. Is that an abbreviation or a spelling mistake? Somebody write in the comments if you know what they're talking about. Before every use, the RCD needs to be reset to ensure the contacts are not freezing together. So we've seen these, right? They could be just a little plug. So it's just got plug on one side, socket on the other. You plug that in, and then you plug in your appliance, and it's got the usually green and blue button. We'll have a little window in there with a red, that's either red or black, to indicate whether it's switched on or not. You also see these as it says there, as part of a cord set, so an extension cord with the RCD built into it. Although the extension cord ones are becoming less common nowadays, they're more likely to find the plug-in ones. They're a bit more portable, and it means that you can plug whatever you like in. You don't have to use that huge lead every time. As it says, they're usually voltage dependent, so each time you plug it in, you'll have to push the reset button. SRCD, a socket residual current device. Again, they're far less common these days than they used to be. We've seen these, right? These are your socket outlet, generally in a bathroom. So these were probably pretty common in the 90s, maybe early 2000s, before it was a requirement that all socket outlets had to be protected by an RCD. But obviously after RCDs existed, so people were installing them in wet and damp situations, bathrooms in particular. And then when the requirements that all socket outlets be protected came in, then we stopped using these generally, because why would I bother? I just put an RCD in the switchboard, and that covers all of the sockets. I don't need a special one at the socket outlet in the bathroom. But this is a socket outlet that has an RCD incorporated in it, and you'll see that by the green and blue button on there, which tells you that that's an RCD socket outlet. Interesting one, something that I've come across. I've talked about this before in class, but something I've come across in my own home recently that I've never seen before is the bathroom downstairs has the socket, the SRCD, the RCD at the socket, and then that the bathroom upstairs is also controlled from that same socket somehow. So they've wired the sockets in the upstairs bathroom to the RCD in the downstairs bathroom, which is weird, and it seems shady to me. It works, but there you go. So you might just come across that one day. One of you might come across that and go, oh, this is really strange, I don't know what's going on, and you'll remember that, and you go and check the other bathroom and find, oh yeah, the RCD's tripped there, and then you flick me a text if that ever happens. Send me a message and say, I just came across a bathroom with the RCD socket like you talked about. And it's a picture of these things. So there's our normal RCD here. Neutral connection is labelled in there. That's important. It needs to be labelled in and out. This is our portable. That's part of a lead. Like I said, you can also just get that bit there. And then this is our SRCD. So that's a socket RCD. So it's got the normal socket outlet, normal switches, and then our test and reset buttons. And again, that little window there, that'll have a red or black. If it's red, that means it's live, so you should have voltage. If you plug something in and it doesn't work, then check the little window. If it's black, that means the RCD switched off, you need to reset it, or there's something that's gone wrong with your appliance and it's tripped. Here is the diagram of what it looks like inside an RCD. But before I talk about that, the second digit for your access code for the test is a 2. Second digit is a 2. Okay, so actually I won't spend too much time talking about this. We must have seen this before. You can sit here and examine this in your own time. Pause the video, have a look. But let's have a quick look at what's happening here. We have our contacts here. We have current coming in through the phase. See the arrow there indicating which direction it's going. Down here to my load. This is outside the RCD. The dotted line is the RCD. We have current flowing through our load. That's our appliance, whatever it is, and that goes back through the neutral, through the contacts in the direction of the arrow. Now we have this winding here, this transformer essentially. It's like a little current transformer that's wrapped around those two wires. What we know about the magnetic fields in our wires, right, is that as current goes through this wire, it creates a magnetic field. It's going to create a magnetic field in a certain direction depending on the direction of current flow, and the opposite in the neutral. In the normal state, the magnetic field produced by the phase will be equal to and opposite to the magnetic field produced by the neutral, which means that the magnetic field induced in this core, in this coil here, is 0. And as long as there's 0, then there's no voltage in that core. So there's 0 magnetic field in the core, and therefore 0 current, 0 voltage in that coil. Now if we have, so here's our earth wire that goes back to our earth bus bar, which is connected to neutral. If I have any current flow flowing through that earth bus bar, then I'm going to have a weaker magnetic field on my neutral and a stronger one on the phase, which means I'll have some magnetic field produced in this core and therefore a voltage produced in that coil. That voltage goes to the tripping device and that opens the circuit. Simple. As soon as I get a voltage induced in this coil, it's going to operate that down to a level of how much? 30 milliamps. 30 milliamps. So what that's saying is I only need 30 milliamps flowing in this part of the circuit here in order to produce enough voltage here to trip this. Or if it was in a medical situation or whatever, 10 milliamps. Tiny. 10 milliamps is 0.01 amps, right? So 10 milliamps flowing down here is enough to produce a voltage for those medical RCDs. It's enough to produce a voltage in here that will trip that circuit. And here's our little test button here. All that's doing is taking some current from the neutral through a resistor. There's our button, and returning it to the phase, or rather it comes from the phase through the button, through that resistor, and then to neutral. So it's just providing a little path around the outside of my coil. So it's going to make some current flow outside my coil, and as we know, as soon as current flows outside my coil, we get an imbalance and this trips. So that's what my test button does. It just creates that imbalance. Note that it's not testing whether the earth back to the switchboard is any good. All it does is test that the device actually operates internally. So it's not a foolproof test. And here's what's happening in the tripped position, which I just talked about. So we get 10 amps flowing this way, it says that 10 amps there, and 9.5 amps coming back because I have a 0.5 amp leakage current there, it says there. So I have a little fault here, and some current is flowing back this way to earth and to neutral there. Doesn't have to be much, it's going to be some. If I produce that parallel path, then some current will flow in it. So 0.5 amp, that's producing a magnetic flux, a magnetic field, which induces a voltage in the coil, which then goes to the tripping circuit, and that breaks the contacts. Simple. And this is the test circuit as I just talked about. Yeah, already gone through that. 3-phase RCD. For a 3-phase RCD, tests on 3 or 4 pole RCD. Oh, hang on. For 3-phase RCDs, tests on 3 or 4 pole RCDs used on a 3-phase supply shall be conducted with a 3-phase supply connected. The test shall be undertaken individually on each phase in turn, with all load connections disconnected, including the neutral, as any standing leakage current on the load side may add or subtract vectorially from the test current. So if I'm doing a test on an 3-phase RCD, then I'll need to connect a single-phase RCD tester, but I'll need to do each phase individually. So phase to earth, phase 1 to earth, phase 2 to earth, phase 3 to earth. So I guess I'll have to make up a little jig to do that. To be honest, now that I think about it, I've never really considered this. I've never really had to test a 3-phase RCD, but there you go. That's how we would do it. Okay, so different types of RCDs. Type A. This is our most common one, and this is the one that we want to use. Type A is the best one, I believe. So the sensing coil responds to AC and DC pulsating current. So that's important, right? A lot of RCDs only respond to AC, which is fine 90% of the time, but you never know when you might, for some reason, get a weird DC pulsating current, like a rectified DC signal. And we would hate for our RCD to not work if something went weird like that and we got that DC pulsating supply. So a type A will have the ability to respond to AC and DC currents. Typical sources of DC pulsating currents are speed controllers or hair dryers containing semiconductors that are triggered into operation. Yeah, so as I said, if we've got a semiconductor in there, we might get some sort of half-wave rectification. We may be using the semiconductor. Remember when we talked about diodes that we said that a diode could kind of be used as a form of dimming, or in this case speed control. The same way, we cut off half the waveform and we lower the speed. So we need to make sure that we have RCDs that are capable of operating in those conditions. As per Regulation 24, and I'll encourage you to go and look at Regulation 24 because that's where it tells us the specifics for RCDs. Point to note here, actually, as I go through this, Generally, when we get into specifics and details of stuff, right, we go to the standards, ACNZS 3000, or more specific standards in specific situations. But for RCDs, for some reason, they've included a lot of detail in Regulation 24. So there's actually more information there about what we need to do than there is generally in the standards. So as per Regulation 24, all sockets and lights must be on RCDs in all domestic and residential installations. The rating must be the following: 1 times current rating, 30 milliamps, 300 millisecond trip time. 5 times the current rating, that's 150, so 30 times 5, 150. 40 millisecond operation time. If it operates at less than 50%, it's electrically unsafe. So that tells us that it must not operate below 15 milliamps. We're going to get way too much nuisance tripping if we did that. This little symbol here, this is a symbol for AC and pulsating DC. So that's that type A coil, or type A type. AC and pulsing DC. So that's literally a diagram of what a kind of symbol for what a DC, rectified DC, half-wave rectified DC looks like. Oh. Crikey. Hold up. Let me go back on this time. There we go. Okay. Sensitivity. So when we talk about sensitivity, the value of out of balance current for which the RCD is set to trip. So sensitivity means the tripping value. So out of balance current means what's the difference between the phase and the neutral current, which will cause it to trip. And like for our normal domestics, that's 30 milliamps, right? RCDs that are installed in domestic situations for personal protection must have a maximum operating current of 30 milliamps. We know that. This is domestic situations in a house. Must disconnect the supply within 300 milliseconds on an AC or pulsating DC fault condition. So we need that type A RCD. Generally, that's a standard one you get off the shelf. It'll be type A, but it is worth checking. Testing of RCDs. So an RCD has a test button facility that will cause the device to trip when a current imbalance occurs between the protected sub-circuit phase and neutral conductors. Remember though that that's a little circuit that's happening inside the RCD, right? There's no reference to outside conditions. So this test is then, it's not a reliable method of proving that an RCD will work on a leakage fault to earth, because an RCD will still trip even when the protective earthing conductor on the sub-circuit is disconnected. That means the RCD will still trip when I push the test button, even if the earth conductor on that sub-circuit is disconnected. So what's the risk there? Well, if for some reason the earth conductor is disconnected, it's faulty, it's broken, or maybe I forgot to connect it myself, then I can push the test button on the RCD will still operate. If I have an actual earth leakage, or I have actual phase to earth fault, well then the earth path back to the switchboard doesn't exist. So my RCD won't operate because there'll be no current flowing back to earth, and therefore no imbalance in the RCD, but there'll still be a voltage present on that on the body of that appliance or whatever it is, so on that earth fault. So I could touch that and get a shock, and the RCD doesn't trip because the earth conductor is disconnected. So therefore, the only effective way of proving and ensuring that an RCD will trip under both AC and pulsating DC fault conditions is to use proper RCD test instruments. We've seen these, right? We've got the big meters up at Tech. What are they? The Fluke installation testers. They do our RCDs for us. If you get an RCD installation tester, then they'll generally have an RCD tester incorporated into it. RCD individual, just a meter that does RCD testing is fairly common as well. Procedures for testing the operation of an RCD. The operation of an RCD installed for personal protection from using electrical appliances shall be verified by the use of A. Test equipment which verifies the operation under the following conditions. At rated residual current for an AC fault, the device shall operate to disconnect within 300 milliseconds. Okay, 300 milliseconds at rated current, which is 30 milliamps. Remember, this is slightly different for those other ones, the 10 millisecond ones. Now 10 milliamp ones for schools and medical facilities. So remember to check the correct ones. Additional info. An RCD has an electronic amplifier section which can be easily destroyed by insulation testers, mega tester with a total voltage of 500 volts or more. RCD units must be disconnected before insulation tests. So if we put 500 volts across that RCD, then the little device in there that actually does the tripping might get destroyed by that 500 volts. So we disconnect our RCDs before we do our insulation test. In residential installations, not more than 3 final subcircuits should be protected by any one RCD. So you can have more than one subcircuit on an RCD, but no more than 3. Remember, practically how this looks in our switchboard is all the neutrals from those subcircuits come back into a individual neutral bar, and then from that neutral bar we go back through the RCD, and then the other side of the RCD goes to our main neutral bar. So we need to have a separate subcircuit or separate neutral bus bar for each RCD. So depending on how many subcircuits we're protecting or how many subcircuits we have, that'll tell us how many RCDs we need. We must not have more than 3 subcircuits on a single RCD. It's good common practice to share power and lighting across a number of RCDs. What does that mean? So don't put all the power on one RCD and all the lighting on another, because then if you trip that RCD, then all your power in the house is gone, or all your lights are gone. If you put half the power, some of your power on one, some on another, some on another, and then some of the lighting's on the first one, some of the lighting on the second one, some of the lighting on the third, then when you trip one of those RCDs, you're not going to lose all of everything. Sweet. Warning labels must be attached near the RCD and the switchboard supplying it. So you must have a label to tell them that there is an RCD there. Summary. An RCD does not provide overcurrent or short circuit protection unless we specifically get an RCD, RCBO, right? An RCD that incorporates overcurrent protection. An RCD disconnects the supply when leakage to earth exceeds a set point, that set point being the rating of the RCD. So we refer to the RCD as the set point. I'll say a 30 milliamp RCD or a 10 milliamp RCD. That's the set point. The core balance system detects current imbalance due to earth leakage and disconnects the supply. So if I have more current flowing in one conductor than the other, that means that some current is flowing back through earth or a different place, maybe through me, and therefore it's going to trip. The RCD limits current through body, preventing fatal electric shock. As I said, if that current's going through me, as long as it's 30 milliamps, then it's going to trip, and that should be enough to keep me safe. I won't die off a 30 milliamp shock. It must be used for personal protection for installations in damp situations, or it must also be used for personal protection in domestic installations and medical installations, and schools, daycares, kindergartens. Lots of situations. That's the end. That is the last slide. All right, last digit for your code is 9. Last digit for your access code is 9. Now you have that, you can race away and do that test. Yeah, look, I think this one's pretty straightforward. I don't have anything else to say about that. We've talked about RCDs a lot. If anything in this is new to you probably haven't been listening, because RCDs are a topic of conversation a lot. Okay, it is what it is. Alright, as ever, if you have any problems, let me know. I will help you out. Thank you for your time. See you at the next one.